All right, so now let's look at the first type of generation of electronic carriers, the intrinsic semiconductor. So again, we've gone through this in the previous section, but I just want to review this really quickly. In intrinsic semiconductors, we have a valence band and a conduction band, and what we're doing is we're exciting an electron from the valence band across the band gap, Eg, to the conduction band. So that electron here is the negative, and it leaves behind a plus charge, and so we refer to that as electron hole. And so when we want to look at the concentration of these electrons and holes, which are our carrier species in these cases, what we're going to do is go back to what we looked at in the previous chapter. And so I'm just going to kind of put these up as a review, but we've talked about these before. So we can look at the concentration. We can find the concentration of these for intrinsic semiconductors by looking at the density of states and also the band gap and the temperature. So we can calculate that, and then our density of state equations, which we've used previously, we can calculate those by knowing the effective masses of the species. And so doing that, we can then get conductivity. So here is the conductivity for electronic conductivity, right? So the charge, mobility, and then the concentration of our species. So N for electron, P for electron holes. And so that's sort of the sum here. So we've sort of looked at how we get the concentration. And so you see that the concentration of these species is temperature dependent. But now let's look at the mobility. So we haven't talked about the mobility for this case yet. So let's look at that. And so for mobility, what we're going to look at is here. So we're looking at wide band materials. And so we're talking about things with a band gap, right? So our semiconductors and insulators. With this, we see that our mobility decreases with increasing temperature, and this is proportional to T to the minus 3 halves. Right? So mobility decreases with increasing temperature for these types of wide band material. And so how this occurs, so why this decrease in mobility occurs is from what we call phonon or lattice scattering. And so effectively the scattering that we have decreases the mobility. So the higher the temperature, the more that electrons are slowed down, or electron holes are slowed down in the lattice, and therefore the mobility slows down, and therefore that would affect the overall conductivity. And so if we incorporate that factor, and this factor, if you're wondering where this T to the minus 3 halves comes from, it comes from the density of states. So that T to the minus 3 halves dependence comes from the density of states, and that's where we get our temperature dependence related to mobility. So if we put that in, then we can approximate the temperature dependence of these wide band materials. So this is applicable for our intrinsic semiconductors that we're talking about here. All right, so while we're on this, we've talked about these intrinsic semiconductors, but let's also think about the temperature dependence of conductivity. So I want you to sort of think about your intuition and what you've learned from other classes. And so take a minute, pause this video after I've sort of explained this, and write your answers to this, and then we will sort of discuss and see where you're at. So think about the temperature dependence of conductivity. We've talked about the semiconductors, but what do you think the temperature dependence is for metals and then insulators? So see if you can come up with how you think the temperature dependence of conductivity relates to these three classes of materials, and then also see if you can come up with why. So what causes the temperature dependence? What's the mechanism responsible for each class of materials that we're talking about here? So go ahead and pause the video, write down your answers to this, and then when you go ahead with the video, you'll see that we'll discuss the answers to this problem. All right, so here is a nice plot showing the temperature dependence of conductivity for metals, semiconductors, and insulators. So you'll notice that here again the conductivity, and we're dealing with log conductivity. So this is because we're dealing with such drastic changes in conductivity. And so you'll see a curve for each of those classes of materials. And so we just talked, and then temperature on the x-axis. Sorry about that. Temperature on the x and log of the conductivity on the y. So we just talked about semiconductors, and we mentioned that the mobility decreases with increasing temperature. But also for intrinsic semiconductors, with increasing temperature, we also have more charge carriers, right? There's more thermal energy, and so more electrons go across the band gap and leave behind electron holes at higher temperatures. And so overall, the temperature dependence, if we factor in both the mobility and the concentration factors, the charge doesn't change, then we see that the conductivity goes up and quite drastically. Again, keep in mind this is a log scale. So conductivity goes up with semiconductors. Again, so that means that the concentration is overriding the decrease in mobility that we have. So now let's go down to insulators. So I know I'm going out of order, but let's look at insulators. So insulators are more or less semiconductors, but with a larger band gap. And so when we look at the temperature dependence here, it's more or less the same, but it can be more drastic, right? So overall the conductivity is lower, but we see the same general temperature dependence. So same thing, the concentration overrides here, right? So the more thermal energy we have in the system, so the higher the temperature is down here, the more concentration of these carriers that we're going to have, and so the higher the conductivity. So we still have those effects of the mobility, but those are being sort of dwindled by the number of electrons or electron holes that we're creating. So that kind of explains the first two. So now let's go to metals. All right, so when we look at this curve, it looks like it's flat, horizontal, right? And so again, if we think back to the concentration for semiconductors and insulators, we have to cross the band gap. And so that is a thermally activated process. In metals, we have free electrons, right? There's no thermal activation of valence electrons. And so the concentration is roughly constant. And so in that case, the concentration term of conductivity is roughly the same, but the mobility is different, right? So that mobility factor still comes in. So the higher temperature you have, the decrease in mobility, right? So those lattice scattering points that we have, and we're going to talk about them more in a second, but those cause the mobility to go down. So basically, interference with the lattice at higher temperatures causes the mobility to go down. So even though it looks flat, keep in mind we're looking at a log scale. So we have a minor decrease in conductivity. So with metals, we always think of those as having a decrease in conductivity with higher temperatures. And that's what we have here. It's just hard to see because we're on a log scale. And so that kind of gives you the idea of the temperature dependence of these materials, and we can relate them back to the different terms in that conductivity equation. And so this just summarizes what we talked about. All right, so let's continue to talk about mobility and how that affects conductivity. And so I want to talk about something called polaron. And so as you can kind of see here on the slide, this is a defect in an ionic crystal. So we're talking about ceramics, so ionic crystals, that's formed when we have an excess charge and it polarizes the lattice. And so by polarize, I mean it distorts the lattice. And so that's what we mean by a polaron. So it has an effect on the lattice around it. And so this image here is just showing that we have an electron in the lattice, an extra electron or charge, and then this red area kind of shows you the vicinity, the immediate vicinity that it affects. So here it's a relatively large area. Over here, this electron has a very a smaller kind of area of the lattice that it affects. And so we're going to look at this idea of a polaron. And so an example of these polarons, this could be an oxygen vacancy, so the lack of an oxygen. This can trap an electron. So when we have an oxygen vacancy, it can trap an electron. And then because of that, the surrounding cations would be attracted to it, right? So we have an extra electron, and then therefore that would attract those positive cations and move them towards it. So that's kind of what this would be showing here over here, right? We have an extra electron at a site, and then that's going to cause the dissimilar charges, so the positive charges, so here, to be closer to it, so move them towards that. And so that's going to distort this area, right? It's going to distort the area around it in the lattice. All right, so let's look at two different types. We have two different types of polarons. The first one I'm going to talk about is small polarons. And so the small, and then you can imagine the next one's going to be called a large polaron. The size here, the small versus large, talks about the sort of area of the lattice that is affected. It doesn't necessarily talk about the strength of that distortion. It just talks about the area that is affected. So for a small polaron, it's a smaller area of the lattice that is affected, but it actually ends up being a strong interaction. So it's a small area but a strong interaction. So here you can think of this small polaron as an electron that's trapped. So it's trapped at a certain site. So here it's trapped at this site here. And so by trapping it at this site, that means that the mobility, if it's trapped, it's going to decrease the mobility, and therefore the conductivity would go down as well. So these sites that kind of trap electrons cause the mobility and therefore the conductivity to go down. And so if we think about this, this trap, this ionic trap that can trap an electron, decreases the oxidation state if we're talking about a cation. So if we're talking about a metal ion, so a positive charged species, if we trap an electron, that's the equivalent of decreasing the oxidation state. Right? I go from, for example, iron 3+ to 2+ when I trap that extra electron. And so since it's trapped there, it has a really strong interaction, so that it's going to take a lot of energy to get that electron to go to another site. But it does so by hopping. So that extra electron could try to hop to another site, but we're going to have to put a lot of energy into that to get that to happen. All right, so here's kind of an example of how this could manifest itself in a real oxide. So for example, we have iron 3+ and then oxygen. That's our kind of lattice. But if we have that extra electron and it's trapped here in this middle atom, that effectively changed the oxidation state, right? So now we have a iron 2+. And so that would affect the nearby lattice. So the extra electron would sort of cause the neighboring anions, the oxygen, to move a little further away. So all these are moving a little further away. And then the neighboring cations would move a little closer away because we have that extra electronic charge. So this is what kind of traps the electron, is by decreasing the oxidation state of the metal. And so the only way that this can move, this defect can move, is if we hop that electron. So there has to be enough energy to overcome and go to a neighboring cation. And that process, changing the oxidation state, as you might imagine, can only happen in transition metal oxides. So only those that have different oxidation or valence states can have this type of mechanism, because they have different valence states. All right. So in doing this, that energy that we have to put in, that energy barrier to this process, is what we call EB here. So that's the energy well, or depth, of the energy it takes to migrate the electron from one place to the next. So that's EB, is that energy that we have to put in. And so that's normally supplied by thermal energy, that KT term that we have. So it's thermally activated. And so the conductivity then is going to be related to thermal activation. And so you see the exponential, and we have the barrier of moving that, which is EB, divided by KT. So that's describing how the mobility is going to change based on this energy term. All right. So with small polarons, we saw that area that's affected is rather small. So it's trapping an electron in a very small place, very locally. The other case is a large polaron. And so here, the area that is affected in the lattice is much larger. So you can see by this sort of sketch here showing the red area is that's affected, is much larger. So it's not localized to one cation. But the actual distortion is actually, the interaction is just a little bit is smaller. It's not as the interaction isn't as strong as the small polaron. So the name can be kind of deceiving when you look at that. And so here, the way we think about a large polaron is you can think of that carrier. So here it's this electron. So in this case, the carrier, the electron here, isn't trapped at one site. So it's not trapped at the cation site. It's moving through the lattice, but instead of being trapped at one of these cations, it's slowed down by the lattice. Right? So that's the kind of difference in the schematic that we think of for this large polaron. It's not trapped, but it is slowed down by the interaction with the lattice. So effectively, if we were talking about an electron then, that electron, which we know the mass of electron, but when it moves through a lattice, the effective mass of that electron becomes larger from those interactions. So in essence, this large polaron is kind of the mechanism by which that effective mass increases. Right? So that's the way we kind of describe it. So if you remember from the density of states equation, that effective mass term, that's what we're talking about here. So it just slows down the lattice. And because of that, the mobility is proportional to T to the minus 1/2. So a different temperature dependence in this case because of the difference in interactions that we have.